Welcome to this beginner's guide to cryptography. You'll gain the essential skills to safeguard data and deter tampering. This tutorial will equip you with a complete, practical toolkit showing you how to implement hashing algorithms like SHA-256 to verify file integrity and secure passwords. You'll master the art of secure communication by building functions for both symmetric encryption and asymmetric encryption with public and private keys. To help learn cryptography skills, you will build a fully functional command line cryptography tool built in Python. And this course was created by a talented member of Hack Club. Hack Club is a worldwide nonprofit network of coding clubs where students learn to code by building real things with code together. Being part of Hack Club means joining a community that believes in the power of youth to build the future and provides the resources, mentorship, and opportunities to make it happen. You can learn more about Hack Club at hackclub.com.
Hey everyone, welcome to this free CodeCamp tutorial. My name is Thanishkka and I'm a Hack Clubber from Georgia. Today, we'll be looking at cryptography. I know all of you are here for some cybersecurity action. So before we get into our project or even touch Python, let me show you something cool. This is a tool called Cybershe. As you can see here, I put in the words hello world as my input. On my left, I have a lot of different options in cybersecurity for what I can do to this input. Right now, I'm going to show you guys a hashing algorithm called SHA-256. Now, for this input, you see this random string of characters that gets generated. But now, let me remove one character. The output is completely different. When I add it back, it goes back exactly to how it was before. This is cryptography, specifically hashing in action. Today, you're going to see how you can hash text and files and check their integrity in Python, how you can do AES and RSA encryption, as well as how you can check the strength of passwords in a more complex manner. And don't worry, this tutorial is completely beginner friendly, but a little bit of Python experience will help. So let's get started. Before we dive into code, let's go over some basics of what we're going to build. Cryptography is essentially the art of hiding information. We're going to focus on three main areas today. Hashing, as you saw earlier, is a one-way transformation. We also have symmetric encryption, where the same key is used to encrypt and decrypt data. Advanced Encryption Standard, or AES, is generally the go-to method for this. Then is asymmetric encryption. This uses a public and private key pair. You encrypt with your public key and decrypt with a private key. Cybershe lets you experiment with all of this before you write any code, so it's great for visualizing what's happening behind the scenes and getting a better understanding. We already got a sneak peek at hashing with SHA-256, but let's break it down some more. Here we have multiple different options for the size. So we can do SHA-256, SHA-512, etc. These numbers tell you the amount of bits, but again, 256 is generally the standard and it is pretty secure. With a hash, you're not going to be able to get the input if all you have is the output, but it is deterministic, which means the same input is going to map to the same output. There's just not really a way to undo it. It also demonstrates the avalanche effect, so removing one character makes the hash look completely different. This makes hashes really useful in real life. For example, when you download software, websites often post an SHA-256 checksum that you can compare against the hash of what you downloaded to confirm that your file hasn't been tampered with. For example, this is from the official Node.js website, and they've posted the SHA-256 checksums of different download versions. Now, when I download Node.js, I can either use terminal commands, or I can use software like I do, like WinMD5, and I can check the hash of what I've downloaded against these official checksums to make sure that I downloaded the correct file. Hashes are also used to store passwords securely instead of saving your actual password as plain text in a database. Next, we're looking at symmetric encryption with AES. So Here we have first the format of our input and our output. Then we have some new fields, a key, an IV, and a mode. I've pre-filled the key and IV, but let's go through what they mean. The key is the secret password that AES uses to encrypt and decrypt. Depending on the mode, it should be 128 to 256 bits. And in Cybershe, we have the option to provide it in any of these formats. I chose UTF-8 just because it's easiest to show and explain. So I have my key here. Then I have my initialization vector or IV. This should be the same size as the key, and it's basically a random starting point that makes sure every encryption looks different, even if the message and the key are the same. For example, if you're using a messaging app, every time you send a message, it's going to use a new IV, so that even if you text the same thing twice, the encrypted version never looks identical, and people can't encrypt your messages. So here, as you can see, I've encrypted with this key and this IV. But now, if I change the IV, I get a different output. And then finally, we have our mode. So AES works on chunks of data called blocks, and the mode decides how to handle messages longer than one block. Cybershe defaults to cyber block chaining, so each block of data is kind of mixed with the one before it to hide patterns. If I switch to ECB, however, it'll encrypt each block separately, meaning identical plaintext equals identical ciphertext. This is not very secure, and it means attackers can spot patterns easily. It's outdated, not really used much. Other modes, like CTR and GCM, are often used today. CTR is used in network traffic, GCM is popular for web encryption. So once I run this, Cybershe shows me the resulting ciphertext, and then I can also decrypt it by using the same key and the same IV, because again, symmetric encryption uses the same key to do both things. Let's make sure we change our format to match whatever we want to do. And great, we now can see in our output the same message that we inputted. All right, let's switch gears from AES to RSA to do our asymmetric encryption. This one looks a little different in Cybershe because it uses a public key and a private key instead of just one shared one. So I have pre-filled the keys here because the math behind an RSA algorithm requires really large prime numbers, so normally 2048 or 3072 bits, and they do need to be mathematically related, so you can't really make them manually. I used an RSA key generator, and again, public key and private key have to make sure that they go together and fit the correct size. So you also see two new values here, the encryption scheme and the message digest algorithm, which goes with this specific scheme. This scheme adds randomness and padding so that the identical message gives different ciphertexts. For this specific scheme, OAEP, which stands for Optional Asymmetric Encryption Padding, it also comes with this hash function that we can choose from. So once I encrypt my data, I get this weird output, and that's because the output isn't raw binary data, but it's trying to show it to us in UTF-8 characters. To make it more readable, I'm going to change it to base 64. We now see our encrypted output. Great! Then we convert back from the base 64 to our raw binary bytes right before we do our decryption. So for my decryption here, this is my private key that I have copy-pasted. Key password is optional. We're not using it in this case. We're using our same scheme and the same hashing algorithm. We've got our message back. So think of RSA like this. Your public key is like your padlock. It's something that you can hand out to people. Anyone can snap it shut on a box to encrypt a message. But the private key is the only matching key that can then open the padlock and decrypt the message. Hopefully, this Cybershe demo helped you understand what we're going to be building in Python in just a few seconds, how it works, and why it's important. Before we code, let's make sure Python is ready on your computer. So open your terminal or command prompt and type in python -version. If you see a version number like I do, you're all set. If not, don't worry because installation is very simple. Just go to python.org/downloads and download the latest version for your operating system. One important thing, if you're on Windows, while you're installing, make sure you check the box that says Add Python to Path before you install. This makes it easier to run Python and pip commands from your terminal. Then, for your editor, you can use any, but I recommend VS Code. So to download it, go to code.visualstudio.com and follow these specific steps. Firstly, I'm going to create a folder on my computer that's going to be storing all of our code. I'm just going to call it Cyber Toolkit. Then I'm going to go to my VS Code. I'm going to open the app folder that I just made. And I'm going to access the terminal here. I want to work inside of a virtual environment. So basically, the main purpose of it is to prevent version conflicts with packages and so forth, but it's just a lot cleaner and easier to work with. So in order to create it, we're going to run the command python -m venb venb and click enter. Now, as you can see, this folder has been created over here that stores scripts and so forth. That's going to make our virtual environment possible. Inside this folder is where we're going to be writing our code. Great. Now, we know that it's finished creating the environment when it comes out and back to this file path, basically. So to activate our virtual environment on Windows, I'm going to say $venv/scripts/activate. Great. And now when we see this venv in parentheses in front of the file path, we know that we are inside of our virtual environment. On a Mac or Linux, I believe the command is source.venv/bin/activate. So run this command if you have a Mac or a Linux. Great. So now that we are inside of our virtual environment, we're going to install a couple packages that we need for our encryption techniques and the password strength checking. To do that, you're going to do pip install and then the names of the libraries. So Cryptography, zxcvbn, and then bcrypt. You hit enter. It's going to just take a minute to install. Great, so now all of it has been successfully installed and we've come out of the command. I'm just going to make a sample file here. I'm going to call it main.py, and just for the fun of it, let's print hello world. And here, I'm just going to say run Python file in dedicated terminal. So it's going to open this file and run it, and we see this hello world in our output. If you don't have this run button, you can also just go to the file, right click, and say run Python file in terminal. That will do the same thing. Awesome! Now the Python is all set up and working. The code following this is going to work the same regardless of what IDE or OS you're using. So let's jump right in. First, I'm going to create a folder inside my virtual environment that is called modules. This is going to contain all of the functions that we use later in our main.py. In modules, I'm going to make a file called hash.py. This is where we're going to be doing all of our hashing. First, I'm going to import the hashlib library. Then, I'm going to try hashing a text string first. I'm just going to call it hello world. Now I'm going to create a hash object. So once I do this, I'm going to call the hashlib library and then call SHA-256. I'm going to say text.encode in order to get the hash value. Now I want to show the output of my hash in hexadecimal, so I'm just going to say hash digest equals, I'm going to call this object that we just created and then call the hex digest function on it. And then finally, we're just going to print out what we have so far. So the SHA hash of our text is hash digest. Awesome. And now you can run it in the terminal. And yeah, we're going to see our hash right here. So now we've hashed a string, but I want to hash full files. So let's comment out this code. I'm going to do control// because I'm on VS Code, but in Python it's generally hashtags or triple quotes to do comments. Then I'm going to use the def keyword to create our function called hash file. Here I'm passing in the file path as a parameter. Then, just like we did above, I'm going to create a hash object. This time I'm calling the hashlib.new constructor and saying that I want to use the SHA-256 algorithm. Now I want to read our file in chunks and then I want to hash each chunk. So how do we read our file? We're going to say open, file path, and RB. This RB means read in binary because again our hash objects expect a binary. I just want to reference this as file, so I'm just going to say that. Then I'm going to have a while loop that's going to iterate through our file until our chunk becomes until it's empty. That's what this stands for. At which point I want to break the while loop. So first we're going to read our chunks by saying file.read 1024, stands for 1024 bytes. And then I want to update my hash object h with each chunk. At the very end, I'm going to return h.hexdigest so that whatever is returned is hexadecimal digits. Great, now let's test this out. In my virtual environment, I'm going to create a new folder called sample files. I'm going to make a sample.txt file here. You can put in anything you want. We're going to go back to our hash.py. We're going to test this. Now for the testing, I'm going to use this if statement. Say if name equals main. And basically the reason we include this is this if statement makes sure that whatever code we write inside of it only runs when we're running this specific file. So even when I'm calling on functions from this file in main.py, whatever is in here is not going to run. So again, I just want a print statement to make sure that our output correctly. So I'm going to say the SHA hash of file is, and I'm just going to call the function here, hash file. And now we want to get the path of this. So we can either do copy path or copy relative path. And this is this file path that we pass in. Now let's run this in our terminal. Now you might see the syntax warning which just says this is an invalid escape sequence. If you get this and you want to fix it, just put an R in front of your file path. Make sure it's enclosed in quotations. But again, you'll see that we get the SHA hash of our file successfully. Now that we've got the hashes, how do we make them useful? Like I mentioned earlier, hashes can verify file or message integrity, and if you've downloaded the correct versions of things. Even if one single bit or pixel is different, the hash will tell you. So let's create another function right underneath hash file called verify integrity. Here for my parameters, I'm going to pass in two different files. This variable hash1 is going to call the hash file function that we just made on file 1. Then hash2 is going to call hash file on file 2. I'm going to print which files we're checking the integrity between. Checking integrity between file 1 and file 2. You can use a new line here if you want better visibility. And now we're going to see if our hashes are equal to each other. Then we will return file is intact. No modifications have been made. Otherwise, we're going to say, or honestly, we don't even need the else here, because when you return something, the function will automatically stop. Otherwise, if we never get to this return statement, it's going to come here anyway. We're just going to say file has been modified, possibly unsafe. To demonstrate this, I'm going to upload 3 image files to my sample files folder in VS Code. So right in there. Now, as you can see, L1 and L2 are identical, and T, it has been rotated, so a couple things have changed. Now, inside this if name equals main, I'm just going to do print, and I'm going to call our function, verify integrity, and we're going to copy paths again. I'm going to take this, copy relative path, use the R again if you need to, and I'm going to get L2 and copy the relative path here as well. So this should return that no modifications have been made because the files are identical. Now for this next one, the file has been rotated. So we're going to take L1 again. And for our second file, we're going to take T. Let's see what this returns. Okay, so checking integrity between Orpheus 1 and Orpheus L2, no modifications have been made. But between L1 and T, file has been modified, possibly unsafe. That is awesome. You have finished all of your hashing functions. We're going to be moving on to symmetric encryption next. Inside your modules folder, make another file called encryption.py. We're going to import everything we need. So first is secrets. This is similar to the random library, but it's a little bit more secure. Then we're going to import what we need for symmetric encryption. So from the cryptography module, so cryptography.hasnet.primitives.ciphers.aead, import AES GCM. So AES encryption, again, our mode is GCM. And then very similarly for RSA, primitives.asymmetric, we're going to import RSA and the padding that's needed for it. And then finally, we're also going to import hashes because we use that. Cool. I'm going to make my function for symmetric encryption now and call it AES encryption decryption. I'm passing in message as a parameter. And first, I'm going to make my key. So I'm going to use secrets module to generate a random key, secrets.tokenBytes. I want it to be 256 bits or 32 bytes because that is generally very secure. And if you think back to our Cybershe demo, we're going to have a nonce or initialization vector that is also going to be randomly created from secrets.tokenBytes, this time with a size of 12 bytes. And then finally, we're going to create our encryption and decryption objects. That's going to be AES GCM. And we're just passing in our key. We're going to be using this AES object in order to encrypt and decrypt now. So first, create a variable for the ciphertext, and I'm just going to use the .encrypt function. I'm going to pass in my nonce, my message, and then for the last parameter, which is additional authenticated data, we're just going to say none. Now, at the very beginning of this, we're going to prepend the nonce as well. Remember, this does not have to be secret. It does not have to be encrypted. We're just going to make sure that we can use the same one for decryption. So, decryption, variable called plain text. Then we're going to call the decrypt function. First, in order to give it the nonce, we're going to say ciphertext. And then in the hard brackets, we're going to say :12. This means up till 12 characters. then we're going to do after those 12 characters. So that's our message. And again, none here. So this is going to give you back your original message in bytes. Oh, and the message that we passed in is most likely going to be a string. So we want to make sure we do .encode so that we convert it to bytes. Now, when we return our message, we don't want it to be in bytes. That's a little hard to read. So we're just going to return it as a hex string. First, I'm going to return the key, and then I'm going to return my ciphertext, and then finally my plain text. And again, this I want to be decoded so that I can see it as a string, just like we inputted. Great. So we're going to run the symmetric encryption now, just like we did previously. Call this if statement. So if name equals main. It's our standard Python entry point, and I'm just going to print AES cd, so we're calling the function, and then pass in any string of your liking. Great. Now let's run this and make sure it works. Okay, awesome. So here, this is our key, this is our ciphertext, and then at the very end, we see our plain text. Now let's move on to asymmetric encryption with RSA. Inside my function, I first want to make my private key. Remember, we use two keys here. The public key generally encrypts, and then our private key is going to decrypt. So from the RSA library, I'm just going to generate private key and then pass in some pretty standard arguments. So public exponent, and then setting my key size to 2048 bits. Then for my public key, this is going to be extracted from my private key. So I'm just going to say private key and then call this public key function. Great. Now let's get into the actual encryption part of it. So I'm going to make the ciphertext variable, and then from public key, I'm calling encrypt. Now inside encrypt, I'm going to take two arguments. The first is what I want to encrypt. So that's going to be message.encode, because again, it's passed in as a string, this encrypts bytes. And we also have a padding scheme. I'm using the optimal asymmetric encryption padding. So if you remember from Cybershe, RSA doesn't encrypt raw data. It first pads this data using a specific algorithm that we're going to pass into this object. That's why we import hashes. Then once that's secure, it encrypts that data. So inside our padding object, we're going to pass in a couple arguments. First is the mask generation function. And I'm going to set the algorithm to hashes.sha-256. There's another argument called algorithm. Again, doing hashes.sha-256. You can also use SHA-1 or SHA-512 if you would like. And then I'm setting this field, which is used for associated data, to none, just like we did for our AES encryption. Great, so now we've finished our padding configuration and encrypted the data. I want to decrypt it into plain text. So here I'm using private key. I'm calling .decrypt. I'm passing in the ciphertext because that's what I want to decrypt now. And I'm going to give it the same padding scheme. Now at the end, I will be returning the ciphertext as a hex string, and then plain text decoded into a normal string. So in order to test this out, let's just say we're going to call the RSA function, pass in a string of our liking. Now let me run this file. Okay, great. So this under symmetric encryption, and then here, all of this is our ciphertext, and then we finally get our decrypted plaintext. Another critical aspect of user security is protecting passwords. So let's create a new file called password.py. The first thing I want to do is a function that's going to check the strength of that password. In order to do that, I'm going to import a function called zxcvbn. So from zxcvbn, import zxcvbn. Then let's get right to the function. So check strength, passing in password as a parameter. And I'm just going to call zxcvbn on that password. Basically, what this does is it returns an object which has several properties about that password. We're going to utilize score, feedback, warning, and suggestions today. So I'm going to set a variable called score to the score part of this object. This is going to range from 0 to 4. A score of 3 or 4 is strong, otherwise it's pretty weak. So first, I'm just going to say if score is 3, we're setting our response to strong enough password, score of 3. If 4, I'm just going to say very strong password and score of 4. Now, else, if it is weak, we want to get the feedback part of the result object. So we're going to say result.get feedback. And then from this feedback, we're going to pull the warning and the suggestions. So warning equals feedback.get warning. And then suggestions, feedback.get suggestions. And I'm going to set my response to be weak password, score of, and score is an integer here. We can only concatenate strings, so I'm going to make that a string. And since it's weak, I also, again, want to display the warning and the suggestions. So to my response, I'm going to add warning. This \n makes a new line, display the warning, and then something very similar for suggestions. Now, one thing to keep in mind is that suggestions are given in a list, so we cannot directly concatenate like we did here. Instead, I'm going to use a for loop. I'm going to say for suggestion in suggestions, response plus equals, and each suggestion separated by a space. Great, and at the very end, I'm returning response. Let's run this function. So I'm again going to do my standard entry point if name equals main. And here, I want to utilize a while loop because basically I want the user to input a password until it is strong enough, in which case we'll break out of the while loop. So I'm going to say password1 equals, and this is the user inputted password. Now, instead of using input like normal, I want to use get pass so that our passwords aren't shown in plain text. So at the top, we're going to do from get pass import get pass. Then I'm calling get pass here. I'm just going to say enter a password to check strength. Then I'm going to call my check strength function, passing in password1 as an argument. And then to make sure they get prompted again, I'm going to say if this function starts with, so if what is returned from this function, the response, starts with weak. So remember, this starts with weak, this starts with strong, and very strong. If it starts with weak, I'm going to print, please choose a stronger password. And then it's going to go back to this input. Otherwise, we're going to be breaking out of the while loop. So let's test this out. I'm first going to enter a pretty weak password. It's got a score of 0. You have my warning, no warning here, and then suggestions. Please choose a stronger password. So now I'm going to do something that's pretty strong, and I get that it is a strong password. I don't see a warning or suggestions here. We just finished checking the strength of a password, but now I want to simulate storing it as well as verifying it to provide or deny access. In order to do this, we're going to import one more library called bcrypt, and we're going to use two functions. So first, I'm going to hash my password. We're passing the password in as a parameter, and first, I'm going to generate a random salt. So this is a unique sequence of bytes that we add to our password before we hash it, just so that it prevents patterns similar to the RSA padding. So in order to generate this salt, we're going to call bcrypt.gensalt. Then, to actually hash the password with the salt, we're going to call bcrypt.hash.py. This is the bcrypt hashing algorithm, passing in our password in bytes along with our salt. And we're going to return hashed. Then we want to verify the password. I want to first pass in the password attempt, so what the user is inputting, as well as the hash password, which is what would actually be stored in a database. So I want to check if they match, and to do that, I'm going to call another bcrypt function, if bcrypt.check password attempt encode. We want to do it in bytes against hashed. So if this is true, then we're going to return password is correct, access granted. Otherwise, I'm going to say incorrect password, access denied. Great, so now let's run this right after we check the password strength. So once our user has inputted a strong password, we're going to hash that password. That might be a little confusing. I'm just going to name it hashed password. I'm calling the hash.py function and passing in this password 1. And then, just so we can see what we have, I'm going to print out our hashed password. But again, because it's hashed, no one can make sense of it. Then we're going to ask them to re-enter their password to verify. And finally, I'm just going to call the verify password function with the attempt as well as the actual hashed password that we have stored, and then print that out. So let's test this. I'm going to first enter a weak password. Again, we see our warning and suggestions. I'm going to choose a stronger one now. And then I'm re-entering it correctly. And yeah, our access is granted. This function and file is working well. This is the bulk of our cryptography toolkit. We hashed text, we hashed files, we verified them, then we did symmetric encryption and decryption with AES, asymmetric encryption decryption with RSA, and then password strength checking as well as hashing and verification. But we still have to put it all together. So let's come out of the modules folder and go to this main.py file. We're going to be importing all of our functions and making a simple command line UI. Let me make this file empty, and then I'm going to do from modules.hash. I want to import hash file as well as verify integrity. We're going to do something similar for all three files. So for modules.encryption, import AES, and then RSA. Then finally, modules.password, import check strength, hash password, and then verify password. Great. Next, I'm going to create a function called menu. This is just going to print out a list of options for the user. I'm going to say select operation, and then we're going to give them a couple different options. So first, I'm going to say hash file. Next, number 2, check file integrity. Number 3, AES encrypt decrypt. Number 4, RSA encrypt decrypt. And then finally, the password manager. If they want to exit out of the menu, we're going to have an option called 0 where they can exit. Great. Now that we finished the menu, I want to print a welcome message to all users when they first run the file. And I pre-wrote it because mine was a little long. So I'm pretending that they are an agent and they are basically on this cybersecurity mission. Now what I want is for our users or our agents to basically see this menu, pick an option, interact with that, and then go back and choose as many operations from here as they would like. In order to implement that, first, I'm going to make this while loop. At the very top, we're going to call this function to display the menu, and then we're getting an input from the user asking them for which operation they would like to run. So if our choice is 0, then we want to break out of this while loop. That's what we have here. Now, otherwise, if our choice is 1, what are we doing? We're hashing a file. So we're getting a file path as input from the user, and then we're going to run the function and print it out. So I'm just going to say SHA hash of file is, and then run the function. Great. Now, if our choice was 2, let's see what we have. We're going to check file integrity. So we're going to get 2 file paths this time. And we're going to call our verify integrity function with both of those file paths. Cool. Now moving on to the third choice, we have our symmetric encryption and decryption. So for this, I first want to get a message as input from the user, and then I'm going to encode it because for encryption decryption we like to work with bytes. Then from my function, if you remember here, we're returning the key, the ciphertext, and the plaintext. I want this to be displayed in a good format, so I'm just going to store them in variables here. So key, ciphertext, plaintext equals, and then call that function. These are the values that are returned to us. And I'm just printing out AES key, AES ciphertext, and then AES plaintext. Cool. Now we'll move on to our fourth option, which is going to be RSA encryption decryption. So we're going to get a message as an input again. And this time, if we look at our RSA function, we return the ciphertext and the plaintext. So I'm just going to store those in variables, ciphertext, plaintext, and call the function. Then I just want to print out the ciphertext. So I'm going to say RSA message encrypted with a public key. And similarly, I'm going to say for decryption, RSA message decrypted with a private key. Show the plain text. Now for our final option, option 5, this is our password manager. So if we go back here, we kind of just want to run exactly what we have here. So I'm just going to copy and paste it. Let's fix our indentation. And we need to import the getPass module, so let's just go up to the top and do that. Awesome. Now, if their choices are not from 0 to 5, let's just be safe and then print invalid choice. Great. So now this while loop is going to be functioning exactly as we intended. And at the very end, after we've come out of the while loop, I just want to print this exiting message. Say, agent, you are exiting your cryptography toolkit. Stay sharp and secure out there. All right, let's just look over this once. I just realized that the message that we pass in here in our functions, we actually pass that in as a string and then encode it into bytes. So in this case, we don't need to do the encoding here. Otherwise, we're passing in bytes instead of a string, and that's probably going to cause an error. Other than that, everything looks fine. So let's test it out and make sure that it works as intended. All right, great. So we see my welcome message here and then our menu. Let's just go in order and check each operation. So I'm going to copy the path, and great, I got the SHA file of it. Now I want to check integrity. So I'm going to give 2 file paths. So one of this, and then let me copy path. One of that. So these should be different. Let's see. So it tells us file has been modified, possibly unsafe. Now let's try again with files that are identical. Okay. So L1 and L2. Yeah, file is intact, no modifications have been made. All right, great. Our third one, symmetric encryption and decryption. Entering a message. Awesome, we see our key, we see our ciphertext, and then back to plain text. I'll do the same one with RSA. Okay, we see our huge encrypted message, and then the plain text decrypted again. And then finally, let's try out our password manager. I'll give a bad password this time. Okay, and then a strong password. Password is correct, access granted, we're back to our menu. Now let's just say I want to exit. And we are all done. Now I just have to say congratulations for building your own cryptography toolkit in Python. But this is only the beginning. You can expand this project with the web interface using Flask. You can encrypt folders and implement digital signatures. You can work with authentication and storing passwords in a real database and so forth. The most important part from this video is that you now understand how these pieces fit together, and you're excited to learn more with tools like Cybershe. Remember, cybersecurity doesn't have to be boring. It is going to be the future. So thank you so much for tuning into this video, and I hope you learned a lot.